Hello everyone, welcome to class 18. So, we will continue with point groups today, and probably so to make the things a bit contextualized in in the context of crystals, real materials, we will probably try to see certain crystal structures where these point groups, how these point groups come up, right. So, we will do a back thing. So, I know the crystal structure, I know how the atoms are arranged in a certain crystals. So, we will try to visualize what are the different point symmetry operations and what point groups exist in this material, right. So, by the end of this class, but first let us start with what we have where we have left off in the previous class, that is we were actually looking at cubic systems and we were sort of overwhelmed by the number of symmetry operations each of these cubic each of these point groups in a cubic system has, right. The simplest point group in a cubic system we said was 2 3, which means I have twofold axis of three twofold axis of symmetry about the orthogonal axis and 4 threefold axis of symmetry about the the 1 1 1 direction. So, if I have to draw a stereogram, so I am just going to put a triangle here, a triangle here, a triangle here and a triangle here, representing 4 threefold axis of symmetry about the 1 1 1s, and there is going to be a twofold axis of symmetry here, there is going to be a twofold axis of symmetry here, there is going to be one here, and eventually one of them which is right smack at the center. So, the 0 0 1 is also a twofold axis of symmetry, right. So, this is the simplest cubic point group, or so I can also look at M 3 bar. M 3 bar is the same as 2 by M 3 bar, right. So, this is the stereogram for this, right. Now, these are the 2 point groups where we will look at examples of this today, where you would have no fourfold axis of symmetry, right. So, again these two are cases where we can so a cubic system that actually prove the fact that a cubic system does not need to have a fourfold axis of symmetry, right. 4 threefold axis of symmetry give you the cube, right, and I am going to show you a case, right. So, of what is called cristobalite, which has a 2 3 sort of point group embedded into it, underlying point group, and so there is no fourfold axis of symmetry there. So, we are going to visualize that at the end of this class. Whereas so we then went on and then said that alright, so then what about if I have a fourfold axis of symmetry, then what happens. So, the minimum point group that we got, I mean the minimum operations, right. So, sorry, the minimum point group we got was a 4 3 2, where if I have, let us say if I even corrupt this cubic system with one fourfold axis of symmetry, then I will have to have three fourfold axis of symmetry, right. So, these are the regular cubic systems that we see where I have 3 fourfold axis of symmetry, and then we said that so the 4 3 2 for example here, so it has maybe I can redraw the stereogram by keeping all these annotations so that you will be able to see it. So, I have a stereogram, so I have these are the axes. Now, this becomes a fourfold axis of symmetry. If this is a fourfold axis of symmetry, this will be a fourfold axis, this will be a fourfold axis, this will be fourfold, this will be fourfold, right, that is okay. But then this is a stereogram, so I will draw the longitudes, and then this is my threefold axis of symmetry, these are my 1 1 1s, right. I am going to color this. So, if I say there cannot be only one fourfold axis of symmetry in a cubic system, if there is one fourfold, that means there are 3 fourfold axis of symmetry, right. So, all the 3 axes become fourfold axis of symmetry, but what you also get for free are these diagonal mirrors, right. So, so this is a 1 1 0, these are all the 1 1 0 sort of directions. So, you will have 4 twofold axis of symmetry here, and you will have 4 twofold axis of symmetry here, right. This is how I represent a stereogram, and now I can take an asymmetric unit and then try to get back, sorry, 1 second, to what I have been showing here, right. So I can try to get back to so this sort of a configuration, right. Now if I ask you the question, does 432 have inversion symmetry in it? I can actually look at one of these points. So let me point out to one of these points here. So let us say I am going to look at this circle here and look at its minus, so look at if a similar dot exists at minus x minus y minus z. If this is a circle, if there is inversion symmetry, so at this position I should find a dot, but I do not find a dot, I just find a circle, right. So which means both these points are out of the plane, they are not so it is not, they are not related by inversion, right. So I do not have inversion symmetry. 432 does not have inversion symmetry, right. So 432 is a non-centrosymmetric point group, it is not a symmetric point group. Okay. Similarly, I have other point groups which are 4 bar 3m, right. So if I have 4 bar, then so there is some inherent tetragonality tetrahedra that are in this structure, right. So I said 4 bar structure, the polyhedron that comes to my mind is a tetrahedron, right. This is 4 bar, right. And the maximum symmetry, the holohedral group of a cubic system is the M3 bar M, sorry, right. So now this is the so this is the point group that most of the FCC metals, for example, right. So this is the underlying point group of most of the FCC metals. Metallurgists, when they talk about cubic crystals, right, FCC materials, FCC metals, the platinums, the golds and so on and so forth, all of them have this as the underlying point group, or silicon for example, or diamond for example, right. So the underlying point groups that exist in all these crystals are M3 bar M. Okay. Silicon, diamond are a bit more complex, but all the regular metals, right. So like the platinums, so the ceramics people talk about what are called perovskites, right. So perovskite materials such as strontium titanate, right. So all these have an underlying point group which is a very high symmetry point group, and that is M3 bar M, right. So this is the holohedral point group in a cubic system. And how many different symmetry operations do I have here? I have 48 different symmetry operations, right. I do not even want to count all of them, okay. Whereas I can visualize them as a stereogram, right. So I do not need to count them, but I could actually visualize them as a stereogram. As you can see here, right. So from this stereogram I have so maybe I can just, so these are the mirror planes, right. So I have 4 so although I am not representing the 4-fold axis of symmetry, I am just calling it M3 bar M, right. So by M I mean these 2 mirror planes, but if I have 2 perpendicular mirror planes, right, and also this one is a mirror plane, right. So the mirror is perpendicular to all the 3 axes, but if I have 3 perpendicular mirrors, I also get the 4-fold axis for free, right. So instead of writing it as 4 by M or something like that, I just write it as M, right. So in fact it is 4 by M 3 bar 2 by M, right. So I have 4 3-fold axis of symmetry, sorry 3 4-fold axis of symmetry, but all the perpendicular axes to them are mirrors, right. So those are the number of symmetry elements. I have 4 3 bar axis of symmetry, and these 3 bar axis are about the 1 right. So these points here, right. So these are all 3 bar axis of symmetry. Then I have all the 1 zeros which are all 2 again mirrors, right. So I have the diagonal mirrors, whatever phase diagonal you take, that is a mirror plane, okay. So these are the different types of operations, whatever diagonals you take, not the phase diagonals, but whatever diagonals 1 bar 0 or 1 0 sort of planes are all mirrors, okay. So there is a mirror symmetry about 1 0 sort of thing, okay. So these are the different sorts of symmetry operations that exist. And if I ask you the question, is there inversion symmetry here, you are going to say of course there is, right. There cannot be something which is more symmetric than this, right. So in fact the mechanical engineers and mechanical metallurgy people, they talk about what are called isotropic crystals, right. So where more or less so this is, you have by isotropy what you mean is I have a 360-degree symmetry, right. So, I cannot distinguish between this direction and this direction, right. So, that typically does not happen in crystals. In a triclinic crystal, I do not have isotropy, right. So, for isotropic crystals, so the cubic system with M 3 bar M symmetry comes close to describing this ideal isotropic system. Okay. So, let us put that down. A cubic system with M 3 bar M symmetry is a good approximation of crystals of materials which are isotropic. So, the properties will be same in all directions, and so, or so the so I take that back. Properties are not same in all directions, but properties are those that so properties can be derived assuming that I have a 360-degree symmetry, right. So, I have rotational symmetry. My crystal is rotationally invariant. My material is rotationally invariant, right. Materials that are called isotropic, right. If I take simple properties, right, so like conductivity or for example, if there is conductivity should be same along the cross diagonal elements, and it should be zeros of diagonal element should be 0, right. So, a second rank tensor should be like this for an isotropic material, right. If I go to fourth rank tensors, it becomes slightly more complicated, but the number of elements in a fourth rank tensor is the minimum for an isotropic crystal, right. So, cubic systems with M 3 bar M symmetry, point group symmetry, come close to are very good approximations of what are called isotropic systems. Okay. There are some differences which we will see when we look at fourth rank tensor later on, but so that's good enough approximation for now. Okay. So, alright, so there is inversion symmetry, everything that is, and all your FCC materials, right. So, FCC metals such as platinum, etc., right. So, gold, right. So, all these crystal structures, all these FCC crystal structures of platinum, gold, etc., they have this symmetry, right. So, they have a point about which I have M 3 bar M symmetry. Now, what is that point? If I am actually looking at the stacking of so this is along the one direction, right. So, these are the 111 planes of 111 planes of let us say platinum in a face centered cubic crystal structure, right. So, these are all the platinum atoms. I am actually representing all the platinum atoms, and so I am also going to say that on the top of this covering this void are going to be my next set of platinum atoms that I am going to put here. Okay. And on the bottom also I am going to put so eventually what I will get here is some sort of a configuration which is so let us say here. So, I have 3 atoms here. Okay. So, maybe I should not use the light pink, sorry, let me redraw that. So, if I am just stacking these atoms, right. So, this is something that is traditionally done as a metallurgy 101 course, where I have these atoms which are sort of hard spheres which are touching each other, and along the FCC 111 I am going to so these are all close packed planes, right. So, what I am showing you here is a close packed plane, right. So, and this is the 111 direction, right. Now, on the top of this I am going to write it with a different color. What I have is atoms that are sort of covering these voids here, this one, and here I have something which is covering this void. Okay. So, so if I look at the red one is forming some sort of a triangular structure like this. The pink one underneath is also forming a triangular structure which is displaced like this, right. So, I have 3 atoms on the top which form this red triangle and 3 atoms on the bottom which form this pink triangle, right. So, in the center what I have is a void, and that void, the structure that I formed here is, so we have looked at this earlier. This is, sorry, I have to go back to the pen. I will redraw this, yes, right. So, these are where the corners are where the atoms are sitting. Okay. All atoms are sitting at the corners. All platinum atoms are sitting at corners. Let us just give it a name. Okay. So, the center of this octahedron, the polyhedron I have here is an octahedron, 6 vertices, 3 on the top, 3 on the bottom, right. And the center of the octahedron is a void. Now, what is that point about which? Now, what is that point in platinum? In the structure of platinum, which is any FCC metal in general, right, that has an M3 bar M symmetry, right. It is the center of the octahedron. Right. So, I have drawn an octahedron here which has a center point, and the central point is what is called the octahedral void, which is supposed to have what is called an OH symmetry. This is what is called Schoenflies notation. We will not worry too much about it, but that means that what I have is about that point, the operations that I have, the symmetry operations I have are M, 3 bar and M, right. Now, 3 bar is easy to see, right. So, 3 bar, why is that point, why does that point have a 3 bar symmetry? Because I have one triangle on the top, the other triangle on the bottom, right. So, of course, about that point I have a 3 bar symmetry, right. But then so I can have a 4-fold axis of symmetry, which is so I am looking at this along the about the 1-1-1 axis, sorry, yeah. So, I am looking at a 1-1-1 plane, right. So, the out of plane is actually the 1-1-1 axis, right. So, I am looking at this along a body diagonal, but then there is another axis that will pass through this, right. So, through the crystal edges, right. So, through the A axis or B axis or C axis, and so I have a mirror that passes perpendicular to that axis, right. And I have a 4-fold axis that also passes through that, right. So, all the point symmetry operations that you can think of that exist in M3 bar M are existing through that point, okay. So, that is the center of your octahedral void, okay. So, that is the simplest explanation in case of an FCC metal, right. Now, let us look at more examples, right. So, an FCC metal has an M3 bar M symmetry, we will come back to that later on, right. But first let us visualize a few more crystals, right. So, what are these crystals that have visualization? Let us do some visualization, right. So, what are these crystals? These materials or crystals. Crystals, I am using it in a very loose terminology, right. So, crystals meaning something that is available that can be mined, and so sapphire is a crystal, for example, diamond is a crystal, and so on and so forth, right. So, what are these crystals in a very a gem kind of terminology, a jeweler type of terminology, right. So, what are these crystals that are cubic, but do not possess 4-fold symmetry, right, or not. What are those crystals? Example of a crystal. okay, and this is our so called silicon oxide. Now silicon oxide, when it crystallizes in cristobalite. Cristobalite is a mineral of silicon oxide, right. Okay. Now mineralogists came up with many different names, right. So depending on so they have their own terminology. Silicon oxide can exist as several phases or several polymorphs. Okay. Now the basic element of all these polymorphs is a silicon oxygen tetrahedron. So this is a silicon SiO4 tetrahedron is a basic element of all the polymorphs of silicon oxide. Okay. Now depending on how you arrange these tetrahedron, right. So there is one tetrahedron here, there is T2, right. So I have to join T2 to T1, I have to join T3 to T2 and so on and so forth. I get different phases or different phases have different symmetries, right. So for example cristobalite is one thing, right. So cristobalite has a point group that is 2 3, right. This is the underlying point group. Then the more famous example is quartz, right. Quartz has a point group that is 3 2. I am going to tell 2 3 is different from 3 2. 3 2 means this is actually a trigonal system. I did not still talk about trigonal system, but quartz is also, just take my word for now, that quartz is also a polymorph of or a phase or polymorph, right. So I am going to use this sort of terminology from now on. Of silicon oxide which crystallizes, but it crystallizes in a trigonal system with 3 2 being the underlying point group, right. So the cristobalite has 2 3, which means it has 4 3-fold axis of symmetry. Quartz only has 1 3-fold axis of symmetry. Okay. So that is the difference. So this is a trigonal system, whereas this is a cubic system. Okay. Then I can also have amorphous silicon oxide, where the underlying unit is still a tetrahedron. But the arrangement of all these tetrahedron with respect to each other, that does not follow any sort of so then I am going to tilt the second tetrahedron somewhere here, you see. So I am going to make a chain of these tetrahedron that are not arranged in any particular order, right. So this gives me an amorphous, so there is no particular translational symmetry here. Okay. So that gives me an amorphous structure. Okay. Now if I just take silicon oxide, right. So silicon oxide I said is a nice tetrahedron, right. Now inside this tetrahedron, so any tetrahedron would remind you of a 4-bar sort of symmetry, right. But I have to sustain, so in one tetrahedron I can find an axis about which there is 4-bar sort of symmetry, right. So I can look at the tetrahedron as there is oxygen here, and then underlying this there is another oxygen here, and in between these two, right. So there is silicon, right, there is silicon sitting here, right. So that is my tetrahedron. So I can have a 4-bar axis of symmetry, not 4-bar axis, but a point about which there is 4-bar symmetry, right. But so for the tetrahedron to for this unit to preserve this 4-bar symmetry, every other unit should be arranged in a very similar fashion, right. So the next unit should also have the same thing, right. So the red one should keep going like this. Sorry, let us just erase this, that is okay. So the red one, red oxygen should keep going like this, the underlying oxygens, right. And the vertical ones should keep coming like this, right. So the pink one is out of plane, and the red one red one is inside or into the plane, okay, and silicon is in plane, silicon is on the paper. Okay, perhaps this blue color I have to change it because it is not dark enough. Okay, so silicon is on the plane, right. So I can have this sort of a very symmetric structure, and then I am going to then I and then I just continue this, right. So without doing any gimmicks, right. So I exactly do the same thing as a molecule offers me, right. So I sort of very loyally represent the molecular symmetry, the symmetry that the molecule offers even in a solid, right. So I arrange all these tetrahedra very nice and fine, right. So if I am going to do that, and then so silicon is going to be put like that, and so my silicon is here, 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 here. Okay, so this is red, sorry. Okay. Yeah. So if I do that, now this entire crystal that I am forming will have a 4-bar symmetry, right. So this will have a 4-bar symmetry, right. Or I retain the 4-bar symmetry. Present in the tetrahedral unit. Okay, but I do not need to retain it, I do not need to arrange all these things in such nice order, right. So, so if I just do this, right. So I have one of them which is like this, and then in between there is my silicon, right, and then so I immediately destroy it by having the second oxygen like this, and then second silicon like this. So there is no so if I am just isolatedly talking about one entity, one silicon SiO4 entity, then there is 4-bar symmetry, but it is not isolated anymore, it is in the presence of the second unit. So this is first unit, this is second unit, right. So here I have destroyed the 4-bar symmetry, okay. So it is so whatever you may have, you may think of, okay, so the tetrahedron. So when I think of 4-bar, I have a tetrahedron, but it is not necessary that if I have a crystal full of tetrahedra, right. So that is formed by joining different tetrahedra, I do not need to retain the 4-bar symmetry, right. So it is much more stricter condition to retain that 4-bar symmetry in a crystal, right. So all these tetrahedra need to be arranged in a certain fashion, okay. Now let us actually then go back to VESTA and see the structure of this cristobalite, right. So let us open this, right. Okay. Now here what am I looking at? So I am looking at, so all these blue atoms are silicon atoms, right, and all the red atoms are the oxygens, right. Now if I am looking at this, right. So for example, I have this is silicon, right. So this is oxygen, 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 oxygen. So all these are tetrahedra, but all these tetrahedra are not arranged in the nice fashion that I was showing you earlier, right. So if I look at it about A axis or B axis, it is not all arranged in a nice fashion that I am showing you, okay. However, if I look at this crystal, right. So if I go to the orientation and then orient this crystal about 1 1 1, right, and then the upward vector can be 1 minus 1 0, and I apply. What I end up seeing is these hexagons, right. So everything is on the top of each other, very nice and cozy, right. Now I am going to argue that this has threefold axis of symmetry, right. So for example, or 3 bar, right. So in that case, sorry, this is just 2 3, right. So, this is just threefold axis of symmetry. So, for example, if I take this point here, right. So, I am going to represent the point here. If I take this point, about this point, there is threefold axis of symmetry. Okay. So, how do I visualize that for myself? I am going to rotate this in plane by 120 degrees. Okay. So, I am just going to rotate it in plane and see that nothing has really changed. Okay. So, okay, the point, okay, so it is not rotating about the point that I marked, but that is okay. But in general, the if I rotate about a point by 120 degrees, nothing really changes, right. So, right. So, that point came here, but so in general the shape of the crystal or the arrangement of atoms, nothing changed. It is as if I did not rotate, right. So, whether, so look, so if you can look at the A, B, C axis here, right. So, I rotate by 120 degrees, yes, once. So, the C came here, A came here and B came here. Did anything happen to the crystal? Nothing, right, and so on and so forth, right. So, it is just the point that I have marked artificially that is rotating, that is to show that I am rotating, but nothing has happened to the crystal, right. So, there is a threefold axis of symmetry, right. So, you can also look at the same thing about 1 1 bar 1, right. So, the other diagonal also will have a threefold axis of symmetry. However, if I actually then go back to the A axis and then see if I have a threefold axis of symmetry, sorry, a fourfold axis of symmetry here or not, right. So, I am going to rotate this by 90 degrees. Okay. So, let me rotate it about the A axis by 90 degrees. Now, here you have to remember some patterns, because so initially for visualization let us remember some patterns, right. So, in this unit cell, the unit cell itself may change, but that is okay. So, I am going to have a pattern where so I have these two atoms, so I have two longish bonds in this projection, although all the bond lengths are equal, right. But in this projection these two look like longer bonds and these two look like shorter bonds and in some sort of weird angles, right. So, I am going to rotate it by 90 degrees and see if I can regenerate this crystal. See, so here what I have now are so it has completely changed, right. So, there is no, so I go back, I see that okay, so this is in this fashion, right. So, I mean, so you can see it there, visually you can see it rather than me explaining it, you can actually see that this is the case, right. So, all these outer atoms are so these are the longer bonds, these are the shorter bonds, but the angles are in a certain way. But if I just rotate it by 90 degrees, the tetrahedron orientation has completely changed, right. So, the same crystal is not regenerated when I rotate it by 90 degrees. Okay. So, there is no fourfold axis of symmetry, but if I rotate it by 180 degrees, I again get back, right. So, it is the same sort of tetrahedra or okay. So, these are the ones, right. So, these are the units that I am seeing, right. So, for example, this one, right. So, the unit cell has shifted, but I am seeing the same sort of patterns again, right. So, it is the same crystal, it can be translated a bit here and there depending on which point I use to rotate, but that is okay, right. So, this is exactly the same crystal that I started with, right. So, there is twofold axis of symmetry here. The way I have arranged the tetrahedra, right, I can maintain 4 threefold axis of symmetry, but I do not need to have a fourfold axis of symmetry, right. So, cristobalite is a case. I urge you to actually download this structure cristobalite from database, right. So, the database can be what is called materials project database, or you have what is called crystallography open database COD. Okay. Look at silicon oxide in a space group which is like P32, I think P312 or something like that, does not matter, but 32 is your point group of interest, sorry 23, I am so sorry, 32 becomes quads then, right. So, this is 23, right. So, 213 or something like that, there is some screw axis here somewhere, but that is okay. So, download this crystal, right. So, in the form of a CIF file, and then you can visualize it using VESTA. Okay. For yourself, you prove to yourself that there are 4 3-fold axes, no 4-fold axis of symmetry, followed by 4, I will just write it as 4, followed by 3 2-fold axis of symmetry, and these are A, B and C. Okay. So, you can just play around, you can rotate this crystal and then prove to yourself that this is the case indeed. Okay. So, with that I will stop here, but in the next class we will actually start by looking at a crystal, again visualizing a crystal where the 4 bar. So, I start with units which are tetrahedra and then arrange them in the way that I have shown, right. So, this is zinc sulphide, right, which retains the 4 bar axis of symmetry. In fact, the point group for zinc sulphide becomes 4 bar 3m. Okay. So we will try to visualize where that point is in the zinc sulphide crystal, and so how are the tetrahedra aligned, right, which is more symmetric than how the tetrahedra are aligned in the case of silicon oxide. So, here also you have zinc S4 tetrahedral units. Just like in cristobalite, I have SiO4 tetrahedral units. Okay. So, all these align such that it just gives a 2-3 sort of point group, right. So, that is the highest point about which there is highest point group symmetry is 2-3, whereas a point about which there is highest point group symmetry will be here 4 bar 3m, right. So, this is more symmetric than this. Okay. So, we will try to visualize it in class, but also I would urge you to download the structure of zinc sulphide and actually see it yourself, right. So, and then come prepared for the next class. With that, let me end here, and I will see you again in the next class.